Welcome to this video. I would suggest putting all these equations on an Excel sheet so you can see how things change very easily. For instance, I use this Excel sheet to put things on, and I say, well, what if I raise my red line to 6800, and I can see how my estimated mass flow rate change, which, as you know on the last tutorial, it's important to know your mass flow rate to know your compressor map and where your mass flow rate might fit in terms of compressor efficiency, and also an estimated amount of horsepower that your vehicle produces. So I'm going to go through by hand and show you the formulas, and you can be free to make an Excel sheet to make things a lot easier to calculate so you don't have to go through a series of equations every time. And it's fun to see, oh, what if my intercooler efficiency became 80%, and see how my horsepower would change, or what if my compressor efficiency goes up to 90, and you can see that volumetric efficiency, if it goes up just 5%, produces a large horsepower change. So you can see what's vital, what's important, what doesn't affect horsepower as much, and so on and so forth. Again, this is garbage in, garbage out, and these are approximating equations, but they're good enough to see what kind of turbo system is great for your car. So let's jump in and see how to do it. The first thing that I want to do is calculate the displacement of my engine. In other words, with every 2 turns of the crankshaft, what is the total volume that my engine will take in and push out? To do that, I care about stroke and bore. If I have a piston here, so my marker survives all of this, my piston has a diameter, and we'll call that bore, and it moves up and down, and the distance that it moves up and down is stroke. This is a very easy number to find, and the formula is also very easy. I have the number of cylinders, so if I have a V6, it'd be this number V6. If I have a V12, that number V12, just the number of pistons times displacement. I'm sorry, that's what I'm solving for. The number of pistons times bore squared times stroke. And I want to divide that by 1.27, and that's the universal number, works for any engine you calculate. In this case, I'll do this for a Supra 2JZ engine, and I'll say 6 cylinders times, it has a bore roughly 3.8 squared, times the stroke of also 3.8, divided by 1.27. And I meant to say 3.38. About 3.38 inches by 3.38 inches. This 1.27 is calibrated to be measured in inches, so you do not have to worry about your units. You do have to worry that this is in inches. So I say 6 times 3.38 squared times 3.38 divided by 1.27. That comes out to be 183.76 inches cubed. So I'm going to write up here, the displacement of my engine is 183.76 CID, or cubic inch displacement. Now that I know my displacement, I'd like to calculate my volumetric flow rate, and I can do that with a very simple equation. I'm going to say displacement times RPM, if that looks like RPM, and then divide that by 3, 4, 5, 6. This number again works for any engine you compute, and it's very easy to assume, or remember at least 3, 4, 5, 6. This equals my volumetric flow rate, and that's going to be an ideal or a perfect volumetric flow rate. I know my displacement is 183.3, or sorry, 183.76, and I multiply that by my RPM. Let's say I redline at 6,800 RPM. Divided by 3, 4, 5, 6. And once again, this 3, 4, 5, 6 is calibrated to cubic inches by revolutions per minute, so make sure you have that right unit. And that's going to equal 360.81. And that's going to be in cubic feet per minute, or CFM. So I'm going to say CFM equals 360.81. It's nice to have this on the spreadsheet because you can calculate any number of RPMs pretty instantaneously. You don't have to sit here and do these calculations for every single RPM. At this point, we've only done a perfect CFM rating, and every car is rated with a volumetric efficiency. And it's a very simple computation to do that. I simply say my CFM is 360.81, and I'm going to multiply that by my volumetric efficiency. I'm going to assume that the Supra is 85% efficient. If anyone's got a more accurate number, put it in the comments section. I'd love to see it. And that comes out to be about 306 CFM. I'll add that on. Now that I know my ideal volumetric efficiency, I'd like to calculate my mass flow rate. And to calculate my mass flow rate, I'll get 2.703, which is a universal number, again, use it with any computation, times my ambient pressure. At sea level, we have 14.7 psi, and make sure that your pressure is in psi. And I'll use my VFR, which is 306 CID. And I'm going to divide that by my ambient temperature. I'm going to assume 85 degrees Fahrenheit, which is a very reasonable thing to assume when you're doing turbochargers, plus 460. 85 plus 460 is 545. And multiplying these, I get a very high number. But divided by 545, I get about 22.3-ish for my mass flow rate. Now this is the mass flow rate for a naturally aspirated engine, and we care a lot more about what the mass flow rate for a turbocharged engine is. And so this will be in pounds per minute. And I'll put an NA right here. And since we care about pounds per minute, we have to do some calculations for the air running through the turbocharger. Let's knock that out. Now the first question that I want to ask myself is, what do I want to use the car for? Is it going to be a street car? Is it going to be a race car? Am I going to tow and haul things with it like a diesel? Am I going to, what do I want to get out of it? And from that, maybe make an estimation of what kind of boost is best to run in your application. And so I want to figure out the pressure ratios of my compressor. And I'll use the formula as follows. With this equation, I said the pressure ratio of my compressor is equal to the boost of my compressor plus the ambient pressure at sea level, for instance, it would be 14.7 psi minus the pressure drop divided by ambient pressure. That's to say that my pressure ratio for my car would be 15 psi boost. And notice this is PSIG, or the PSI that you would see on a gauge. This boost does not count ambient pressure. So I could rewrite this to say, in other words, this equation saying boost PSIA, which means that the PSI accounts for the ambient pressure. That would be 15 pounds of boost plus the ambient pressure minus the pressure drop of the components divided by the pressure ambient is equal to this equation, which this PSIG does not account for ambient pressure. So I'll say 15 psi plus ambient pressure 14.7 minus, let's say my intercooler drops 1 psi and my air filters drop 1 psi. Usually you can find the pressure drop ratings of an intercooler in the information that they give you before you buy an intercooler. And then divided by 14.7. And that comes out to be about 1.98. So almost twice the pressure inside the intake tube as in the surrounding air after the air exits the compressor and the intercooler. I will write that here. The pressure ratio of the system and we'll use that for later. The next thing that we want to do is figure out what kind of temperature is coming out of our compressor. So let's calculate that. To gauge the temperature coming out of the compressor, I can use this formula. Please do not be intimidated by it. It is not hard at all. I'm going to assume that the temperature outside is 85 degrees, which is a pretty standard assumption in terms of when you assume things in turbocharging. So I'm going to say 85 degrees Fahrenheit, and I have ambient temperature over here too, so 85 degrees Fahrenheit, and I have ambient temperature right here, 85 degrees Fahrenheit, and I know the pressure ratio of my system. In that case, it's going to be 1.98. And now, all I do is I solve this part first, and then I say minus 460 minus 85, and then I divide by efficiency and plus 85. What is this efficiency? This is the efficiency of my compressor. I can assume that my compressor for my application is 75% efficient. Once again, that's a turbo-specific number depending on what compressor you decide to go with. And when I do the math, it'll be 0.75, of course. That's how we compute percents. So to do this, 85 plus 460 is 545. I just computed this, times 1.98 to the 0.283 power. So I just move this down here. And when I compute that, I end up with 661. So between these parentheses, I have 661.23. Then I say 661.23 minus 460 minus 85. That gives me 116.23. 116.23 divided by 0.75 is 154.97. I'll round that to 155. 155 plus 85 degrees is 239.97. I'll make that 240 degrees. That is hotter than boiling, and it's no wonder why we need things like intercoolers to help cool that air down, because 240 degrees Fahrenheit will expand air quite a lot and destroy the density that we need. I'll write this up here. And moving on to the next equation. Now that I'm using an intercooler, I'm going to want to find the temperature coming out of the intercooler. And in order to find the temperature coming out of the intercooler, I needed to know the temperature coming out of the compressor. So it's a good thing that we found that. Here's the equation to find the temperature coming out of the intercooler. Nice simple equation. I have what is the efficiency of the intercooler multiplied by the temperature of the intercooler coming out minus your ambient temperature. In this case, we've assumed 85 degrees ambient. So I can assume, let's say I have a 75% efficient intercooler times the temperature of the compressor coming out. We know that that is 240. And I'll subtract my ambient temperature. Computing 240 minus 85, I have 0.75 times 155 degrees Fahrenheit, which will give me 116.25 degrees Fahrenheit. Notice a very significant and substantial drop in temperature. This is the reason why intercoolers are so effective and good for turbocharging. I'll write my temperature of the intercooler out up here. Now that I know my temperatures coming out of the intercooler, we can assume that that would be the manifold temperature. And now I want to calculate my density ratio. Since turbocharging really matters in terms of density, let's calculate the differences of density between the ambient air and what's going into our engine. So to calculate that, I'm going to say my density ratio equals the pressure ratio of the system, and I'm going to multiply that times a fraction, and that fraction is going to be ambient temperature plus 460. And I can divide that by temperature of the intercooler coming out plus 460. I know my pressure ratio is 1.98. I'm going to multiply that by 85 degrees Fahrenheit plus 460 divided by 116.25 degrees Fahrenheit plus 460. Computing that, I have 1.98. 85 plus 460 is 545. 116.25 plus 460 is 576.25. Dividing these two, I get 0.94577 times 1.98, which is 1.8726. Notice my degrees Fahrenheit here and here canceled out to give me a constant. So my density ratio is I'm 1.8726 times more dense going into the engine than I was before. And this is a really big determining factor of the kind of power that I'm going to make. So I'll write it up here. Okay, so if we recall, our mass flow rate was 22.3 pounds per minute. And now I know my density ratio. My density ratio was about 1.98. And yep, you guessed it, I simply multiply them together to get 22.3 times 1.98, which will equal about 44 pounds per minute. Horsepower is extremely easy. I simply multiply my mass flow rate by 10, and that is roughly the horsepower that I get, which will be roughly 440 horsepower. And that's how you can calculate mass flow rate and horsepower. And once I find mass flow rate, I simply plug that in with my pressure ratio that we've also recently found, and that will give us an ability to read our compressor map and figure out what kind of horsepower we're going to get. Now I can consult Bing. There's a great Borg-Warner compressor map. Let's see if I can find it. I clicked Maps. I should probably do Images. There we go. The Maps tab isn't the map that I'm looking for, sadly. I'll go Borg-Warner EFR 7064. This is a compressor map for it, and we just calculated that I've got 44 pounds a minute, which is a round red line, so it'll be right around here, at a compression ratio of 1.8. I simply connect the dots, and I find that at red line, I'm sitting right here at the edge of this compressor map, so I'm not quite I'm not quite stalling right here, and I can calculate my other RPMs and come up with a really nice map. I'm not going to do the calculations by hand again, so I'm going to say 68. I'm going to change this to 3.38 to get a correct stroke and bore. And notice before I calculated 15, it gives me 447, so my spreadsheet rounds a little bit differently than what I did by hand, and that's okay. All I have to do now is say I want my RPM, let's say if I'm fully spooled at 3000 RPM, I'll have a mass flow rate of 19.75. And if I'm fully spooled, I'll still have a compression ratio of 1.8. So at 1.8, I'll be at 19.75 pounds per minute, about right here. So right when I'm fully spooled, I would hit this beautiful efficiency island and go all the way back. And it looks like I can tune this for very high compression ratios. 15 would be just the beginning, and get some great results. So this is an excellent compressor map and a compressor for the 2JZ engine. Again, it's about looking through tons of compressor maps, finding the best one for you. I hope this video was helpful. Please post any questions and I'll get to them as best as I can. Thank you for watching. If this video was helpful, please subscribe, and I'll catch you next time.